system, you see two evaporators, evaporator 1, evaporator 2, and also there are two compressors, 1 and 2, and there is also a flash tank, which is used for intercooling. And also you see a liquid line is being separated. So here the purpose of this flash tank is to intercool and also to separate liquid. Okay. Both evaporators, they are working at two different temperatures, 5 degrees Celsius and -30. And also their capacity is different. That is 200 kilowatt of heat is absorbed here. For example, 180 kilowatt is the capacity of this refrigerant is ammonia. Throughout, refrigerant is ammonia. One evaporator is providing this much at this temperature. The other evaporator is at 200 kilowatts at 5 degrees Celsius. The system uses two-stage compression with intercooling and is arranged as in figure. So figure is given here, this schematic. Calculate the power required by the compressor. This is part A for this system. Second part is also calculate the compressor power if separate compressors serves each evaporator in a single stage compression. So this part B is saying that calculate the power if we have a separate compressor for evaporator 1 and a separate compressor for evaporator 2, no intercooling, no flash tank, just two separate compressors, this one and one condenser. Condenser is the same. And here you have another compressor, which is sending directly to that condenser. There is no intercooling. So both compressors are separate. Okay. This is part two. Then we will compare the power. Which system gives higher power or less power? Which consumes more power or less power? Okay. So let's first solve the first part, which is this one, which is shown here. So these symbols should be clear. This is actually a symbol of a float valve acting like a throttling valve. This is a throttling valve. This is a throttling valve. So all these three are throttling valves. So what will be the power of compressor for this system? M dot 1 into H2 minus H1, yes, plus M dot 3 H4 minus H3. That's what we need to find out for this system. Okay, so we'll find out enthalpies and then mass flow rates, which is flowing through this lower evaporator and then from the higher evaporator. But here some mass is also coming, some mass is coming from here. So that will give us this M dot 3. Okay. So to find out enthalpies, first thing what we do is to show it on pH diagram. Okay, let me draw pH diagram. cooling or what? 2 dips into a cold fluid, then rises up and go to high stage compressor, right? Okay. I'm also joined online. Can you see the screen? Nobody is joining online. Did I share the screen? I think no. Now you can see. So I'm recording it. This part was not recorded last time. Again, pH 1 to 2, then 2 to 3 is cooling, then 3 to 4, another compression, 4 to 5, condensation. Now here 5 to 6 and 5 to 6. Same 6 means same pressure and temperature. And it is throttling 5 to 6. Okay. Then 6 to 7. Both are 6. Why both are 6? Because both are at same pressure and temperature. But this 6 divides into 2 parts. Liquid is separated and gas is separated. So 6, 8.6, 7 is liquid separation. Which 6? This 6. And 8.7, we have another throttling till 0.8, and 8 to 1 is evaporation. Okay. But 8.6, the other 6, we have completed this 6 to 7. What about this 0.6 here? Yeah. Is happening. What is happening? This 0.6, this 0.6 is entering into a high temperature evaporator. So 6 to 3, this one is evaporation at 5 degrees Celsius. So 5 to 6 are actually 2 processes. 5 to 6 here and 5 to 6 here. This 6 to 3 is not only evaporation, but also from this point 2, some mass is adding up here. Okay, so mass is coming from high temperature evaporator, and also mass is coming from point 2, which gets cooled down and merge here. So the lowest temperature evaporator is -30. Condenser temperature is given 40. All these temperatures are within the dome. Okay. Within the dome, when the phase is changing, here temperature is 30, here temperature is 5, here temperature is 40. Any issue so far? Okay. So here is the pH diagram. Now there are three pressures. This is the total power of compressor. So let's calculate first of all enthalpies. Easy. H1 is equal to Hg at minus 30. 4.2. Tell me quickly, 4.2. Pressure, P2, and second line, temperature. Temperature, I do not know. 0.2. Of course, pressure, no. How I know the pressure? Yeah, this is P set at 5 degrees Celsius. And I need another line to fix 0.2. So this is pressure. What is this line? Entropy. So entropy is S1 is equal to S2, which is equal to Sg, this one, at minus 30. So if you can trace these two lines on a pH chart, we can fix 0.2. And then we can read enthalpy. Okay, so let's see. So here he is writing all the pressures corresponding to these three temperatures. These are saturation pressures, which we can see from table A3, which is ammonia table. So H1 is equal to Hg, S1 is equal to Sg at minus 30 from the table. It's easy. H2, let's see it again for H2. I need this entropy line and this pressure line. This entropy line is this one, 6.06, or just start from this minus 30. There is some entropy line going on. So go there. So at minus 30, draw a line parallel to these entropy lines. Second was pressure. How much? I think 500 something. So here is the second line, pressure line. This is 0.2. So how to read enthalpy? Draw a vertical line. So about 1630 here, vertical line. So 1630 from HS chart. So 0.2 is done. Now 0.3 is easy. 0.3 is simply Hg at 5 degrees Celsius, or this pressure 517 kilopascal. Okay. 0.4. Same procedure. 0.4 pressure is this one, which is already here. 1557 kilopascal. And what is the second line? Entropy. S3 is equal to S4 is equal to Sg at 5. This one, Sg, which is equal to S4, isentropic compression. Okay. So that will give us 0.4. So here is, this was 0.2. Now this was 0.3 temperature. And here is the entropy line. And this is the highest pressure. I don't know how much it was. So what it was, 1200, 1400, something, 1450, whatever. So this is 0.4. This is 0.2. This is 0.3. This was 0.1. 1 to 2, 2 to 3 cooling, then 3 to 4. Second compression. Draw another line, so that will be enthalpy, vertical line. That is about 1625. 1620. This was 1630. Now it is between these two, so 1625. 1625. H4. Okay. So that's what all we need. H1, H2, H3, H4. But now we need to find out m dot 1 and m dot 3. Yep. Enthalpies on the compression side we have calculated, but now how to find out m dot 1? M dot 1 is the mass which is flowing in the low stage compressor here. And here it is m dot 3. How to calculate m dot 1? This is minus 30 and its power is also given. I think 200 kilowatts. This is 200 kilowatt capacity and this one I think 180. This is the refrigeration capacity. So can I find mass flow rate using this? If you are preparing for test 1 on Monday, then you should know how to calculate mass flow rate. Or you will start preparation on weekend. Temperature. This QE, which is 200 kilowatt, I can write it as m dot 1 into okay, so you will study on weekend. Delta T. H1 minus H8. This is given 200 kilowatts. H1 we already know. H8 now I need. So from here I can find out m dot 1. Total capacity is given and m dot 1 is to be calculated. Question? Okay. So then m dot 1 so we need H8 now. So how to calculate H8? Tell me quickly, it's so easy. H7 is equal to H8. Equal to where to see? Hg at, yes, at 5. Hg, Hf. So now from here I can find out m dot 1. Now m dot 3. M dot 3 is not that simple because at point 3, fluid is coming from low stage compressor. Fluid is coming from high temperature evaporator. Fluid is also coming from flash tank. Let's see. Point 3, we need to see the schematic to find out m dot 3. Let's go to the schematic. Here you see. So m dot 1 I simply calculated using this capacity. Okay, the lower one was 180 kilowatt. Now what about m dot? This m dot 1, this was m dot 1. It goes here, then it rises up. So this m dot 1 is reaching here after cooling down. But during this process, when it cools down, it heats this fluid. So maybe some more vapors are evaporated with this m dot 1. So here what is rising? M dot 1 plus some more vapor which may be evaporated, plus this vapor which is coming from here. And here there was a division of this M. So here it is some unknown vapor is coming from here also. Okay. So here is, okay, if we say Mu unknown here, this Mu unknown here, this M1 we have calculated. This will give us M dot 3. Okay. So M dot 3 depends upon this component and also this component, both. So let's make a system boundary across both of these and write energy balance, because M dot 3 is dependent upon this and also this. So we shall draw a system boundary. I will define a system like this. Okay. And write energy balance and mass balance to find out M dot 3, which is going into the high stage compressor. So for this system, now this is my system. Inside this red line, every other thing is surroundings. So what is entering into that system? This is entering. This is also entering. This is leaving. And this is also leaving. I have included both of these into my system. That's why this is leaving. Any other thing entering or leaving? Okay, let's write what is entering. M dot 2 energy balance. Energy entering is equal to energy leaving. So energy entering is M dot 2 H2 at 0.2, and energy which is entering at 0.5, which is divided into two parts, but within the system. I have included it within the system. So plus M dot 5 H5. This is the energy of the mass entering. Any other entering? Yeah, what is this 200 kilowatt? Yeah, is it entering or leaving? Entering, because this 200 kilowatt is the energy absorbed by that evaporator. So this is also entering Q dot E. So plus 200 kilowatts. That is the heat energy absorbed by this evaporator. This is kilowatt, so every other term should be kilowatt. So here M dot, if it is in kilograms per second multiplied by what is enthalpy unit? Kilojoule per kilogram. So it is kilowatts. So that is kilowatt, kilowatt, kilowatt. Okay, what is the energy leaving? What is leaving here? At 0.7 and at 0.3. And these are massive leaving. So energy of the mass. M dot 3 H3 plus M dot 7 H7. Okay. This is one equation. So we'll see if we can, enthalpies are already known. M dot 2 is known. Okay. This M dot 2 is known. Is M dot 2 is equal to M dot 7? See the figure? Whatever mass is flowing here, it is finally reaching here. So M dot 2 is equal to M dot 7. So here I can write this m dot 7 as m dot 2. Okay. Similarly, see here, m dot 3 is equal to m dot 5. Yeah, this mass is finally reaching here at 0.5. After that, it divides. So here m dot 3, this m dot 5, I can write it as m dot 3 because m dot 3 is equal to m dot 5 and m dot 2 is equal to m dot 7. Okay, so now in this equation, enthalpies are already known. M dot 2 is known. Only unknown here is m dot 3. It's the only unknown. You do not need mass balance. Only energy balance can give us the unknown m dot 3. This is the only difficult step in this chapter. Every other thing is very similar to what we did in chapter 2. So it's clear that that's how we calculate m dot 3. By writing energy balance on a system which we will choose appropriately. Right. Any question? So let's go back to the solution. We were here. Okay, enthalpies are clear. So this is m dot 8, which is equal to m dot 1. Yep. That is from this QE. Okay. So m dot 7 is equal to m dot 8 is equal to m dot 1 is equal to m dot 2. All right. At point 3, it will be different, but these are all same. Then for the high temperature evaporator, and there is also intercooler, 6 to 3 is not only an evaporator, but it is also an intercooler. Okay. That's why we separated that to find out m dot 3, which is leaving. And here this is important. 200 kilowatts is also entering. So that's what I explained. So just put values. So here this will give us m dot 3. Look, m dot 3 is higher than m dot 2. Almost double, more than double. Because there is another evaporator. Now we can find out work of compressor. For low stage, m dot 1 into H2 minus H1. M dot 1 into H2 minus H1. And m dot 3 into H4 minus H3. Low stage, high stage. And you can see here high stage compressor work is high because m dot is high. So that is the total work input required for that system. Okay, so using such thermodynamic analysis, we can find out the power of compressor, which is required in this system. When we want to have two refrigeration system, one at 5 degrees Celsius, other at minus 30. So tell me, what is this 200 kilowatt? From where it comes? From Yeah. How you calculate? It's given, yes. If it's not given, then you found how? Uh, how? Yeah. Your project is telling us this thing. To cool this room at 5 degrees Celsius, how much heat has to be removed? That is chapter 9. To find out the heating or cooling load, that is this 200 kilowatt or 180 kilowatt, which you are seeing here. That is your cooling load calculation. But now it is our requirement because if it is air conditioning room, then you do not need to cool till 5, but your evaporator fluid is at 5, but room is not at 5. Okay. But this evaporator, this lower one, this cannot be used for air conditioning because here temperature is minus 30. So it means this particular evaporator is used for freezing of foods, and this upper one is used for air conditioning of a room. Okay. And this 200 kilowatt or 180 kilowatt, a separate heat transfer process which you are doing in your project. Okay, the part two of the same question. Part two of the same question was that each evaporator has its own separate compressor and no intercooling. So what this mean for the part two, there is one condenser, same one condenser. Now fluid is going first to this evaporator E1, and some fluid is going to E2. Second part is saying both evaporators have their separate exclusive compressor. So this evaporator is sending this fluid to this compressor, and this evaporator is sending to fluid to a separate compressor. Both are not linked to each other by any way, like in this question. So this compressor will directly send it to this condenser, and this compressor, C1, C2, this will directly send to the same condenser. Maybe like this. This is second part. No intercooler, no flash tank. Both have their own separate compressors, but condenser is one, same condenser. So let's draw its pH for this system. So what we do normally, we number it. Let's number it 1, 2, 3, 4, 5, 6, and 5 to 7. Now let's draw its pH diagram. Schematic is clear. Both evaporators, both have their own compressors, and both of them are directly sending the fluid to the same one condenser. Now let's show it. Now 1 to 2. So here is one condenser. So 1 to 2 directly to this condenser. 1 to 2. And you have another compressor at a higher temperature. because this is at high temperature. 3 to 4. 1 to 2 and 3 to 4. Because this is a low temperature evaporator, this is some high temperature evaporator. Then at 0.5, that is 0.5, what happens? There is expansion 5 to 6. Is there any liquid vapor separation? No, there is no flash tank, there is no leak. So then there is 5 to 6 and 5 to 7. But you will show it like this on pH diagram. So 6 to 7 is actually nothing, but it looks like there is a process 6 to 7. So actually it's 5 to 6 and 5 to 7. Yep. So put arrows or do not put arrows. Show arrows, but correct. If you show it the other way around, it's a big crime. Okay. Yep. So now you have to find out the power for this compressor, for this system. So what will be the power? Yeah, here again m.1 plus now you can see the differences in both pH diagrams and which enthalpies will be different and which enthalpies will be same. One will be same in both of these. One will be same. 2 H2 will be different. In this case, H2 was till this pressure, but now H2 is going till this 40-degree. Temperatures are same inside the dome, 5 and minus 30. So 0.2 enthalpy will now be different, corresponding to the pressure of 40. 0.2, H2 will be different. What about H3? H3 on both systems will be same or different? Same. And 0.4, H4. Yeah, I think same. H4 will be same. Here and here. No. Why no? That was the old system here. But 0.4 is not disturbed. 0.4 is at same pressure and same entropy. Yeah. Because look, 0.4 is starting from 0.3. This 0.3 is saturated liquid. Here we cooled this 0.2 to 0.3. So what will be different is m dot. But H, which is per kilogram, that will be same. M.3 in this system will be different from the previous one. But what about H3 and H4? Those will be same. I say yes. H3 and H4, which were here, it will be same here. Okay. So far only H2 you have to calculate again. By extending this entropy line up to the pressure corresponding to 40. Before it was corresponding to 5. What about H5? Is it same as before? Same. H6, same. 0.7 is shifted. There is no 0.8 now. This 7 is actually continued till here. So what will be H7? H5 is equal to H6 is equal to H7. Right? Which is HF at 40. Okay. So the questions, if you draw schematic and pH correctly, then things are much easier. Yep, because some students, they make mistake initially somewhere here in the schematic or in pH, then everything will be wrong. Okay, so what else? So you can find out enthalpies. Now, what about m dot 1 and m dot 3? Is m dot 1 same as here? No, he's saying same. Look, yes. This is not the reason. Okay, how we find m dot 1 here? From Q dot E, which was given 180. Yeah. Is equal to m dot 1 into H1 minus this, the previous part, H1 minus H8. But now it will be Q dot E, yes, m dot 1 into H1 minus H7. And H7 is different. So m dot 1 here will be different. Okay, what about m dot 3? Oh, the dome is gone. Okay, let me show. Draw. Okay, m dot 3. In the previous case, it was very complicated thing because fluids were coming from here. But now it's, I think, simple. Fluid is coming only from this evaporator. So use the same equation. Q dot E is equal to m dot 3, which is coming from only from that evaporator. Now in this case, so it will be m dot 3 into H3 H6. Yes. So calculate m dot 3. So here in this second part, it's easier because mass is coming only from evaporator. In the previous case, it was coming, some was coming from evaporator and part was coming from intercooler or flash tank. All the enthalpies are known. So these new mass flow rates you will calculate, and power input to the compressor. All over. Yeah, m dot is not same. M dot 3 now will be different. Even m dot 1 is also different because 0.8 changed to 7. So both m dots will be different now. Okay, so that has been done here. This was m dot 1 after calculating enthalpy H1 and H4. Okay. For 0.2, this is the pressure corresponding to 40 and entropy. I have shown it. Let me show you on pH that this new point 2. This was previous question. Low compressor and then high compressor. Now in this case, low compressor, this line will continue here to represent this brush, right? The same low compressor is compressing till this. This will be so it is out of this chart. If you extend this the same and copy it to minus to pressure. So hopefully in the exam I will not give such thing which will be outside the paper. But so this comes out to be 1810. Okay. So this was part 1. Now for part 2, now just we saw this is enthalpy H2. So this is clear. This point 2 will be 1815 kilojoules per kilo. So the power of this compressor is simply m dot into H2 minus H1. Now for the high stage compressor, first calculate m dot 6. Okay, first calculate enthalpies. H6 is equal to Hg clear. H7 again, it's the same as previous one. H8 will be equal to H3. Okay, it is using different numbering, which I did before. Okay, so here is the m dot 6 from QE, this one, 200 kilowatt into is equal to m dot 6 into H6 minus H8. Okay, so from here, m dot 6. That will be used to calculate compressor power, which is here m dot 6 into H7 minus H6, H7 minus H6, 29.4. Now total power, just add this compressor power and this compressor power. This comes out to be 97.6 kilowatts. In part A of the question, it was 91, I think. In part 1, it was around 91 kilowatts. But now there is no intercooling. Both evaporators, they have their own compressors. The compressor power has increased to 97.6. Okay. Any question? Yeah, as far as the power saving is concerned, part A is better. That's why we use multi-stage compression with intercooling. And that flash tank was also separating liquid. Here you see 0.4 has more vapor. Before in the part 1, this was shifted here and then it went here. So refrigeration effect was also even better. So we didn't calculate COP. If you calculate COP, so you will see COP of the previous system is definitely better than this one. Okay. So these were the tables and charts used for this question. Okay. Now the last topic of this chapter. Okay, so in this entire chapter and also in the previous chapter, we were using one particular refrigerant. Either it's all ammonia or all R22, right? So in all these systems which we have seen so far, like this one, single stage or multi-stage, uh, the fluid was only one. But there is certain limitation. Can we have another stage? Or we can have another stage? Yes, but if this freezing point of this fluid is very low, and what is this point? Critical point. So if you have a fluid with a very high critical point and very low freezing point, then we can operate in this region. You can have evaporation and condensation, but above critical point or below freezing point, these processes are not possible. And why we are so much interested in evaporation and condensation? Because during evaporation and during condensation, heat transfer capacity of the fluid is much larger. And also, because all these are what? Heat exchangers. What is evaporator? It's a heat exchanger. Fluid is entering here, leaving here, and absorbing heat. And this heat transfer equation, this heat transfer from this fluid to this fluid, yeah, what was that equation of heat transfer from heat transfer course? MCP delta T is thermodynamic. Heat transfer. Heat is transferred from this air to this fluid through that piping. Yeah, UA delta T. U A delta T, which is equal to MCP delta T. Now, see here. What is U? Who remembers U? Overall heat transfer coefficient. Okay. And U further has on this side, you have a fluid on inside. Okay, this is outside fluid, this is inside fluid, and there is a wall. So this U has all those effect 1 over HI plus 1 over HO plus delta X over K, remember? And we want, if we want smaller area, this U should be very high. And U will be very high if these are very high. And if you remember, these are highest when there is boiling or condensation. These convective coefficients, they are highest during phase change. Okay. That's what we saw one table in chapter 1 of heat transfer. That these convective heat transfer coefficients, they become very high when there is a phase change. So that makes U very high and it makes area very small for the same Q dot. That's why we always want, this is another reason to have evaporation and condensation during heat transfer, right? So, but to have this evaporation and condensation, you should be below the critical point of that fluid and higher than freezing point of that fluid. So you should be operating between these two limits. If your required temperature is very low, or the critical temperature of that fluid is very small, then you may not be able to operate within this dome. You may have to go outside the dome, which is not recommended. So you have to choose a fluid in a way which has very low freezing point and very high critical point. Okay, if it is not, then we have to go for multi systems, two different fluids. Just like in power plant, we are studying two different fluids, gas and vapor, or two different vapors. Okay, the ones who are in power. Okay, same is here. Okay, this has been discussed. Let's see here the common refrigerants which we use. For example, this R12, that is its chemical formula. Look at its freezing point. Minus 58, minus 158. And that is its critical point. So minus 158, 112. Our condensers, our condensers ever operate around 112. It will always be below 112. So that's why this is an ideal fluid to operate in this extremes, minus 158 and 112. And this is very important thing. What is this boiling point of this at 1 atmospheric pressure? This fluid will evaporate at minus 29 at this pressure, 180. If you compare this fluid properties with water, freezing point of water is 0. So you cannot use water as refrigerant below 0. It will be frozen. And look at the boiling point at 1 atmospheric pressure, 100. So if you want to use water for evaporation, so it means you have to operate this water system under vacuum. Only then you can make this water to boil at, for example, minus 29. To make otherwise, water will never boil at minus 20, it will freeze. So you can never use water at such low temperature. But I can use water at 5 degrees Celsius, but you have to drop this pressure. You have to operate under vacuum. Okay. And critical point is very high, so there is no issue with the critical point. You can have a condenser at any point. Okay. But these are the issues with water. That's why this is excellent. Now see here R22, another very commonly used. Look at its freezing point, just like this one. And also the critical point is also much higher than normal condenser temperatures. And the boiling point at minus 40. Boiling point is minus 40 at 1 atmospheric pressure. I am feeling cold. So that's why these are very ideal fluids, because to evaporate them at 5 degrees Celsius, for example, I want to evaporate these two at 5, not minus 29. Do we need to create vacuum? You have to pressurize, because at 1 atmospheric pressure, its boiling point is minus 29. So you have to pressurize, not to create vacuum. Pressurize is okay. It's not that bad thing compared to create a vacuum and to maintain that vacuum. Because vacuum, if you create such low vacuum, always air will try to enter. Once air is entered, it's gone. Pressures are disturbed. So that's why these three fluids which are shown here are R12, R22, and ammonia NH3. They have excellent thermodynamic properties. Their freezing point is very low. Their boiling point at 1 atmospheric pressure is also low, in minus low, below 0. And critical point is also okay. So that's why these fluids are normally used, these three, in majority of the air conditioning systems. Even at a 1 atmospheric pressure, you do not need to create vacuum to achieve such low temperatures. Okay. Compared to water, that's why water is not feasible. We can use water, but you have to create a very large vacuum, and below 0 is not possible for water. Now this is CO2, that is another type of refrigerant, which we saw in chapter 1. But here the problem is freezing point is okay, very low. But at 1 atmospheric pressure, it is gas. It will not evaporate. It will already sublimate at minus 78 at 1 and 1 atmospheric pressure. So at this atmospheric pressure and at this temperature, CO2 is gas. Look, its critical point is too low. Right? Our condenser temperatures are much higher, 50, 60, 70 degrees Celsius. So that's why we are using these refrigerants. But again, we have to see the limitation. You can operate under these extremes, critical and freezing point. If you use R12 for -100, do we need to create vacuum? I want to use R12 as an in the evaporator at -100. Do we need to create vacuum? Yes. Why? Because boiling point at 1 atmospheric pressure is -29. So if you want to produce cooling at -100, so it means you have to decrease the pressure. Okay. So for example, if you want to use a system where I want -100. Okay. Okay, let me say not -100. I'm using the same example. Let me say -75. I have to create vacuum in these 4 cases. Yes, if I want -75 degrees Celsius evaporation. Here I have to create vacuum, 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 vacuum. Water is of course not possible below 0. But here I do not have to create vacuum for CO2. But issue with CO2 is that you cannot condense it. When here you have a compressor will increase its temperature higher than ambient, then it will be gas, all gas. You cannot condense it. So maybe I should go for -75 to, for example, 20. And at 20, it condenses. It can condense because it is below critical point of CO2. But how it will condense? It will reject its heat to another fluid like this one. And that will be condensing there. So you are using CO2 here to create very low temperature evaporation. But for condensation, you are not going to use CO2. CO2 is rejecting its heat to another fluid, for example, R22. Same as heat exchanger, same as in a power plant, we were using 2 fluids. So here you have on pH diagram, 2 pH superimposed. One is CO2 has a very low critical temperature, and the other is R12 or R22, which is higher critical temperature. That is called multi-stage system. Okay, I discussed everything here. Now you have lower cycle, a different fluid, another cycle, different fluid. And this is actually a condenser for this one, but evaporator for the upper one. This heat exchanger is evaporator for this cycle, upper cycle, and condenser for the lower cycle. This is called cascade vapor compression refrigeration system. Cascading, it is called. It's TS or pH. Okay, let's draw. Let me draw TS first. For the lower one, 1 to 2 is evaporation. Now he's showing like this. We were showing like this, so he's showing like this. So from 1 to 2, 1 somewhere here. This is evaporation. 1 to 2, 2 to 3. compression, 2 to 3, 3 to 4, condensation, 4 to 1, expansion. Okay. For the upper cycle, 5 to 6. What is this? Where this 3 to 4 is rejecting its heat to a fluid which is at temperature lower than 3 to 4. This 3 to 4 is rejecting its heat to where? 5 to 6. So 5 to 6 is somewhere here. 5 to 6. And then 6 to 7, compression. Second fluid. Then 7 to 8. And then 8 to, okay, 0.5 will be here. Actually, domes are different. Here I should show a separate dome for the upper one. Two different domes, two different fluids. Is it okay? So the condensation is taking place, outside condensation is taking place here. And this is the evaporation at very low temperature. Here we are using a separate fluid. There we are using a separate fluid. Okay. Thanks. It is shown here. Look, if you were using only one fluid, then the process would have been like this one. If there is only one fluid throughout. But now there are two fluids, so that's why this is going like this. This is one fluid and the second fluid is here. So this is a decrease in condenser work, condenser heat, and how in the single fluid, this 0.8 will end up here after throttling. But now it is here and then this, so here increase in refrigeration effect when we are using two fluids instead of one single. Okay. Okay, so we'll finish it in the next class. It's called cascade refrigerant. There are no problems for this one in this course. This is for the MS level course where we have problems related to cascades. Want to end?